As we've seen, solving systems of equations can be kind of tedious. It involves a lot of bookkeeping. Now let's look at a trick to use matrices to reduce the amount of bookkeeping necessary to solve one of these systems of equations. For example, let's say we've got x plus 2y plus 3z equals 6, at 2x minus 3y plus 4z equals 3, 3x plus y minus 5z equals negative 1. Let's take this system of equations and rewrite this using a matrix. The way we'll do this is we take just the coefficients. So for the first row, we have 1x, we have 2y, 3z, and then equals 6. Now to keep the 6's separate from the others, the 6 was not a coefficient, it was the right-hand side of the equation. Sometimes we like to put a line or a dotted line in here. And when we do this, this is called an augmented matrix. This part right here is the coefficient matrix, and we're augmenting it with the right-hand side in our system of equations. So for the second row, we keep the coefficients, 2, negative 3, 4, and the right-hand side is 3. And then for the bottom equation, 3, 1, negative 5 equals negative 1. Now comes the actual algebra part of reducing this matrix. If you recall, we had really three basic things we can do to systems of equations. And these are going to be reflected in so-called elementary row operations for matrices. The first thing that you can do is you can switch two equations. That's not going to lose you any information. It's not going to introduce new solutions. If we switch these two equations, we're just writing one of them in place of the other. So as far as if you translate that into matrix language, that lets you switch two rows. That's our first elementary row operation, is you can switch two rows. Next, you can multiply both sides of one equation by any non-zero number. And that doesn't lose you any information. It doesn't give you any new solutions or throw any old ones out, because you can always undo it just by dividing by that scalar. So you can multiply that. If you look at that in matrix language, that means you can multiply a row by any non-zero scalar. Multiply a row by a scalar. And finally, this is really the big one that actually we'll use most often, is you can add any multiple of one row to any other row. Or in the case of equations, add a multiple of one equation to any other equation. But in terms of rows, we can add a multiple of one row to another. That's what actually lets us sort of cancel and get rid of those x's in the other two spots. So our goal in this is to take this. Remember what our initial goal was to rewrite this system of equations as an easier one. To rewrite it as x plus some y's plus some z's equals a number. And then our second equation had no x's. It had a y and some z's equals a number. And then our last equation was z is a number. Right, our goal was to get it to look like this. So as far as matrices are concerned, we want our matrix to eventually look like 1, and then a number, and then a number, and a number. In our second row, we want no x's. We want a y and then some number of z's equals whatever the right-hand side is. And then for our bottom row, we want no x's, no y's. We want a z equals some number. Once we have it like this, we can translate it back into the system of equations and then do the back substitution method we'd done previously. So let's take a look at this example and see if we can do that here. Now, our goal is to get a 1 in the upper left, and we have that. So I'm just going to copy that row. That doesn't need to change right now. We keep the 1, 2, 3, and 6. Now, in the second spot, we need to get a 0 here. So in order to zero this out, what I'm going to do is multiply the top row by negative 2 and add it to the second row. So negative 2, so now I'm using rule number 3. I'm adding a multiple of one row to another. Negative 2 plus 2 is 0. Let me do that in black. Negative 2 plus 2 is 0. Negative 4 plus 3 is negative 7. And then negative 6 plus 4 is negative 2. And then for the right-hand sides, negative 12 plus 3 is negative 9. So that takes care of the middle row. We have a 0 here. We also need a 0 in this spot. So let's, to get rid of this 3, we can multiply the first row by negative 3 and add it to the bottom row. So negative 3 plus 3 is 0. Negative 6 plus 1 is negative 5. Negative 9 minus 5 is negative 14. And negative 18 minus 1 is negative 19. Okay, so now at least we've cleared out the first column. Now we need to make some more headway in that second column. So your goal here is to get a 1 in this spot. Now if I do that on the second row, I'll have to multiply the second row by negative 1/7, and that's going to introduce fractions. And I'd rather not deal with those unless I have to. So let's look at the bottom row. Maybe we can switch the two rows. If we were to get a 1 in this spot, we'd have to multiply by negative 1/5, and we'd still wind up with fractions. So maybe getting a 1 here, maybe we can hold off on that a little bit. It's more important to get zeros down below. So in order to make this a 0, what we can do is multiply the second row by 5, multiply the bottom row by negative 7, and then add the second row to the bottom row. Right? I'm then multiplying each of these rows by a scalar, and then I'm adding the second row to the bottom row. So for now, the top can just sit. If we multiply this row by 5, we get 0, negative 35, negative 10, negative 45. If we multiply the bottom row by negative 7, we've got 0, 35, 98, and then what is that last one? 7 times 19 is 133. Okay, now we can add the second row to the bottom row. So 1, 2, 3, 6. The bottom row now becomes 0, 0, because I'm adding these two together, and then negative 10 plus 98 is 88. And then if we add this negative 45 to the 133, we get 88. Now, these are kind of ugly, but what we can do is we can multiply this row by negative 1/5 to get rid of all those negative signs and to reduce things down a little bit. This becomes 0, 7, 2, 9. Okay, now we're making some headway. Now we want to get a 1 in this spot, so we can divide the bottom row by 88. So the top row can just sit there. The second row, 0, 7, 2, 9. 0, 0, 1, 1. Okay, now this is basically in echelon form, because we at least have zeros down below here. Now it's not perfect because we have a 7 here, but it looks like there's no good way to do this without introducing fractions. So this form right here is called row echelon form. Row echelon form has 1s along the diagonals and 0s all below. Row echelon form is nice because you can use it. You can translate this right back into a system of equations and do back substitution to get your solution. However, sometimes it's not great because we're going to have some division in there, probably have some fractions. So what we'll do instead is we'll reduce this into so-called reduced row echelon form. This one is even better because here, once we get this into row echelon form, we still have to do some back substitution. If we can reduce this matrix further so it looks like 1s along the diagonals, 0 below, and 0 above, and then a number here, a number here, a number here. If we can reduce our matrix to look like this, if you translate this back into a system of equations, this says 1x plus 0y plus 0z equals a. 0x plus 1y plus 0z equals b. 0x plus 0y plus 1z equals c. So this gives you your solutions without any more work whatsoever. Let's actually do that on this matrix right here. Let's further reduce this to get it into reduced row echelon form. That means I need to get zeros above also. So for starters, we've got a 1 in this spot. Let's clear out everything in the same column. So my bottom row can sit there. what we'll do is we'll multiply the bottom row by -3 and add it to the top row. So we multiply this by -3 and add it here. Let me change that to black. We multiply this, we get 0 plus 1 is 1, 0 plus 2 is 2, -3 plus 3 is 0, -3 plus 6 is 3, so that's better. And we can also multiply this row by -2 and add it to the middle row. So that'll leave us with 0 plus 0 is 0, 0 plus 7 is 7, -2 plus 2 is 0, and -2 plus 9 is 7. So now it's looking better. And now the middle row is actually much better now, because now we can divide the middle row by 7 and we've got no fractions. So let's go through and do that. We'll keep the top row as is. The middle row will divide by 7. And the bottom row we can keep as is. Now we can multiply the middle row by -2 and add it to the top. So that'll give us 0 plus 1 is 1, -2 plus 2 is 0, 0 plus 0 is 0, -2 plus 3 is 1, and now the other two rows are already in the right form, so we'll just let them sit. And now we have our matrix in the right form, so this tells us x equals 1, y equals 1, z equals 1. So we've got our solution without any other work. So this is the method of Gaussian elimination, or once we've gone past row echelon form, this is actually Gauss-Jordan elimination. We're using the method of Gauss-Jordan elimination to completely solve a system of equations written as matrices. So we'll look at more applications and examples of this in future videos.